Okay, moving on to question 3. Again, you see my email there on the front page if you have any questions about this particular marking scheme. Okay. So in an investigation into the decomposition of hydrogen peroxide solution using a manganese oxide catalyst, the volume of oxygen produced was monitored with time. 0.2 grams of powdered manganese was added to 50 centimeter cubed of H2O2, and the volume of gas produced at regular time intervals was given below. Draw a label diagram of an apparatus that could have been used in this investigation. So you have your reaction vessel with hydrogen peroxide and the catalyst. Okay, 2 marks for that. You have a method of ensuring a correct start time. For example, the catalyst in the neck of the horizontal flask. You bring the flask to vertical and start the clock. Or the catalyst in a small test tube in the flask. You mix and start the clock. Or you just add the catalyst, the stopper, and start the clock. Any one of those 3. Okay. Then you have the delivery tube is connected to a gas collection system, okay, which is either your upturned graduated cylinder or a syringe, and you have a clear method of measuring your volume, which is either syringe or inverted graduated cylinder. Okay, so you have 4 things are necessary there to get the 8 marks. Okay, we have an example here of what a diagram could look like, and that's where you have the flask sideways. Now that is a round bottom flask, but a conical flask is fine as well. Okay, so that's an example of what a diagram might look like. How would you ensure that the reaction was started at precisely known time? So you have the catalyst, so you have it in, you must have it in your diagram, and then you have to talk about it here, you have to write about it in this part. So this is the one little bit of it focused in particular. So for the first part, it's just the diagram, and here you have a bit of an explanation. So you have the catalyst in the neck of the horizontal flask. You bring the flask to vertical and start the clock, or you have catalyst in a small test tube in the flask. You mix and start the clock. So 3 marks for that. Plot a graph of the volume of gas produced versus time. Okay, one of those readings is incorrect, and what value would you expect to be correct? What was the average rate for the reaction, and find the instantaneous rate of decomposition of H2O2 at 4 minutes. And you correct your graph for that part, so you ignore the incorrect reading for this part when you're getting the instantaneous rate. Okay, so first of all, with drawing your graph, this is where you get the marks. You get the labeled and scaled axes for 3 marks. So you have time or minutes or volume or centimeters cubed. You have your plots plotted correctly for 6 marks. So that's with the labeled and scaled axes, you either have the x-axis labeled time or minutes, and you have the y-axis labeled volume or centimeters cubed. Then you have your points plotted correctly. Obviously, you have the one correct one, so you don't. That's okay. You have the curve drawn then for 3 marks. Okay. So you'll see when we get onto my diagram, I have it corrected. Okay, we can see here is our incorrect reading. Now, if your graph is drawn to include that point, that's fine. You get the marks there. Okay, so if it's a little bit like has a little bit of a kink in it, that's okay. All right, so you get the marks if you include that as part of your graph. All right, so it works better to get the instantaneous rate if you have it drawn like I've drawn it in the diagram. All right, so the 64 centimeter cubed, or the 6 minutes, is the incorrect value. So then the expected value, then anything from 72 to up to about 80 would be accepted there. The average rate then is 86 over 10, because the maximum amount of gas produced was 86 centimeters cubed, and that was reached after 10 minutes. Even though you can see the graph keeps going on until 12 minutes, but the 86 centimeters cubed was reached after 10 minutes, so your average rate is 8.6 centimeters cubed per minute. And then you have your instantaneous rate. You can see how that worked out on the graph there. So I did my tangent to the graph at 4 minutes. I got 2 points on that tangent, and I got the slope. I got 9.5 centimeters cubed per minute. So I've given you a range there of 8.5 to 10.5 centimeter cubed per minute. Now, you get 3 marks for a good tangent, or 3 marks for calculations based on data points from the tangent. Okay, So if you got outside the range, if you've done a good tangent or you've done a good attempt at calculation, you'll get 3 marks there. Okay. Then the temperature of hydrogen peroxide was measured as the reaction proceeded, and it was found that there was an increase in temperature. Draw a reaction profile diagram for this reaction. So there's an increase in temperature as it proceeded, which shows that it's an exothermic reaction. Okay, so you have your reaction profile diagram for an exothermic reaction. So 9 marks for that. So you have your X and Y axis, so you have energy on the Y axis, time on the X axis, or progress of reaction. Either one of those two is fine. You have a suitable curve with the energy of the reactants greater than the energy of the products, and then you have label your delta H and your EA like so. So 9 marks going there for 2, 3, 2, and 2. So 2 for labeling, 3 for your graph, and 2 for putting in your delta H, and 2 for putting in activation energy in some way, shape, or form. So mark clearly on your graph the curve you would expect to obtain if the reaction was repeated using 25 centimeter cubed of the same solution of H2O2 with 25 centimeter cubed of deionized water added. The same mass of manganese oxide was used to justify the shape and position of this curve relative to the graph you have plotted. So here we have, it's the blue graph there, down in the bottom part of that graph, part E is written on it. So you have the curve drawn with the following. It rises to half the height, it's less steep at the start, and it levels off later. Okay, and you justify that. So it's less steep at the start due to lower concentration or slower rate of reaction. It levels off later due to a slower rate of reaction or lower concentration, and it rises to half the height due to the concentration of HCl being halved. All right, so any one of those is fine. So any two, mentioning any two of the shape and position and justifying any one of them, it gets you the 9 marks. And that is question 3.